Okay, this is the setup and solution to problem 3. In this problem, we have an interior of cells and it's surrounded by a shell of alginate. So we're going to have a solution where we have concentration versus radius, and we have R2, which is the exterior of the alginate. We have R1, which is the interface. And for this, we're going to solve for concentrations, which I'm calling Ci, the interior, which is defined over 0 is less than R is less than R1, and Ce, E for exterior, where R1 is less than R is less than R2. And if I have anything marked as Cx, then the x can mean either E or I, depending on the context, but it's the same expression. The solution will look like this. Our boundary conditions are that the surface is held constant, the interfaces meet at a value which we're calling, so the surface we're calling C2 because it's at R2, and then the interface there is a well, it's not a constant value, but it is the same value for both the left and the right solution, and we're calling that C1 at R1. And then the other boundary condition is that the slope is 0 at r equals 0 for C sub I. So setting this up, this is the partial differential equation for the interior, and you've seen this many times. This is just the fixed second law in which we have a consumption term, and this is the linearized Michaelis-Menten expression, which was in the problem that I called Problem 1 Revisited. And these are the boundary conditions. So we have a constant value, C1, at the R1, and then the slope is 0 at the center. If we take this, we're going to let the time component go to 0, because we're going to look only for the steady state solution, and express out our Laplacian in radial coordinates. So that gives us this differential equation. The exterior problem is very similar to the interior, except that now there's no consumption term because it's just diffusion, so it's fixed second law. And the boundary conditions are that we have a constant boundary at R1 and a constant boundary at R2. Taking that and transforming it into radial coordinates and getting rid of the time-dependent component to make it just an ordinary differential equation, we get this expression. Now we take that and we're going to use dimensionless quantities. So we're going to replace the have a dimensionless position, which is R divided by R2. So rho will go from 0 to 1. We're going to have chi sub I and chi sub E being dimensionless concentrations, where we took chi sub I is equal to Ci divided by C2, and chi sub E is equal to Ce divided by C2. So we're referencing everything to the concentration on the exterior surface of the alginate. We have a non-dimensional or dimensionless Michaelis-Menten parameters. We have a nu and a kappa that we use. And these we're referencing the concentration relative to the exterior. And it's necessary to pick that because we need the C2 in here for the equation to have the C2s cancel and make the math easier. And then we're using the diffusion coefficient of the interior to reference the to non-dimensionalize the Michaelis-Menten expression. And then kappa is Km over C2. So again, we're referencing it to the interior. And that the substitution changes our original differential equation into this and this. So this is the ordinary differential equation for the interior and the ordinary differential equation for the exterior. And these are the problems that we had performing our substitutions. So this is the first component for the interior, which gives us this, and then here is the same or very similar for the exterior using these expressions, which gives us this term for the first term in the Laplacian. The second term in the Laplacian will look like this. So you get this term for the interior, and the second term in the Laplacian for the exterior equation is analogous. It's this. Looking at the Michaelis-Menten expressions, the Michaelis-Menten consumption term here in non-dimensional form is this. So that lets us transform the interior ODE into this expression. And the boundary conditions, chi sub I at rho is equal to R1 over R2. So that is at the interface between the two, is equal to Ci over C2, which is at R is equal to Ri, which is equal to C1 over C2. So the ratio of those two boundary concentrations. So that means this is our first boundary condition. Rho I, chi sub I at rho is equal to R1 over R2 is equal to C1 over C2. And then looking at the derivatives, we get an expression for the second boundary condition for the interior, which is that d chi I d rho at rho equals 0 is equal to 0. And then going to the external problem, this is the new external ordinary differential equation in terms of dimensionless variables. The first boundary is that chi sub E at rho is equal to R1 over R2 is equal to C1 over C2. So that's, again, saying that the expression, the solutions have to be equal at the interface. And then the second one is that chi sub E at rho equals 1 is equal to 1. So that's saying that on the surface it has to be equal to C2, which is C2 over C2, which is 1. And that gives us this first ordinary differential equation for the interior with two boundary conditions, and this ordinary differential equation with two boundary conditions for the exterior. So we'd like to solve that, but this and this, if we solve it, we wind up with a term C2 C1. And C1 is something that we don't know the answer to inherently, and the reason that C1 value persists is because we don't have enough boundary conditions. So in order to get the boundary conditions to work right, we have to recognize that there's another physical constraint, and that physical constraint is that the flux on the left and the right hand sides of the interface for the interior and the exterior, this flux, they have to be equal. And for that to be true, we get the flux, set them equal, add rho is equal to R1 over R2, and that gives us this additional equation that we need to solve. So this is going to tell us the slopes at the interface for the interior and the exterior depend on the ratio of the diffusion coefficients. Now, here's kind of where I'm going to jump ahead and say I took this problem and put them into Mathematica and had it solve it analytically, and then I took and I solved this problem, and that allowed me to have an expression for the interface. And when you do this, and I've got the Mathematica document that I can give you, this is the solution that comes out. So it's analytical, and that's great news. I did a change in the coordinates because I find that, and that took a little bit of effort, but it works out really well because now the dimensionless concentration in the interior and the exterior are both a function of these ratios. So we have a ratio which is the ratio of the diffusion coefficient on the interior divided by the diffusion coefficient on the exterior, which is eta. We've got this psi, which is the square root of 2 nu over kappa, our dimensionless Michaelis-Menten parameters, and then phi, which is the ratio of the radius 1 divided by radius 2. And that gives us solutions in terms of these and in terms of rho. So that means that if we get a solution, we can write the solution out purely in terms of the these physically meaningful parameters, and we'll have 3 parameters total, so we can write out actually an entire set of solutions. And when you do this in Mathematica, you actually get a very nice plot, and you can see solutions that look similar to this. So this is the solution to problem 3, and it's worth commenting on that this assumption significantly simplifies the problem and is what allows us to have an analytical solution. What we need to do now is we need to go back and we need to reconsider the true expression. So problem 1, in which we're looking at a numerical solution, and consider the difference between the analytical solution with the approximate Michaelis-Menten and the analytical solution, the numerical solution with the true Michaelis-Menten. So that's going to be the next problem we work on.